high dimensional data type?
Actually, it's kind of important, I think, to distinguish us at times too. Can you hear me up the back? The mic's working? Good, you don't hear anything. Because we sometimes get mistaken for one another for some, I don't know, strange reason, or here they thought that we were husband and wife. I had to clarify that, so just to intercept any problems of confusion for this meeting, I thought it was worthwhile making the distinction. At this, first of all, I want to thank the organisers. It's really lovely to be invited here, and it's been a lovely workshop so far. And it's going to be a lovely few months. I'm a little nervous talking in this group, and partly that is because we're going from one extreme to another. This talk has not a single equation. So I hope you can still follow me. Anyway. Okay, I actually had recorded some bumps in the night, but my audio doesn't work for this slide, it seems like. But just imagine there's some bumps in the night behind this. And I want you to think about, would you walk across Mattingly Avenue, or Mattingly Road, with your eyes closed? No? So why do we do statistics, computer science, mathematics with our eyes closed? Boggles me. But it seems that this is something that we need to improve. So if we continue here, we might find that there's an elephant in the room if we had opened our eyes. Okay? All right, so there's a few themes that run through this presentation. First thing is draw pictures, draw pictures, draw pictures, and get your eye involved. Second one is we're not just looking for the best view. Okay, we're looking for all sorts of other views as well, and the goal is to get some understanding or intuition for the space that we're working in, the structure in the data, how the model looks in the data space, and a chance to discover something new, right? So it's not a focus on the best view. We're going to be looking at lots of views. And another last theme is that everyone seems to be doing a good job of making plots of the model, well, more or less, but this, and even getting the data in the model space. But there's a very little, it seems to be, on viewing the model in the data space. Okay? When you teach regression, you always draw the regression line in amongst the data. You wouldn't think about teaching regression, simple linear models, without also showing residual plots and talking about residual plots. This is the analogous part of that, is we want to look at how the data shape and the model shape compare. It also gives us another way to cross-check whether the model matches what my eyes perceive in the data problems as well. Okay, so those are the three themes. I'm only going to use one hammer today, and Ed did a nice job of introducing that. I'm just going to use tours, which basically I'm just looking at random projections of high-dimensional spaces, and not very high-dimensional for the most part. I'm just going to stick with pretty low-dimensional spaces. Maybe towards the end of the talk we can discuss the large P, small n. I've got a few things to say for that. But. All right, so I don't need to really say more about tours. I think it's random projections, and I think we've seen some examples before, and it seems that people are using them in all sorts of other places as well. Maybe not stringing them together in tours like we're doing. And then I've got the software that I'm using is R. A lot of people use R for their computational engine. GGoby is the interactive and dynamic graphics engine, and RGGoby is the glue that binds them, so you can script interactive and dynamic graphics from R. Okay, so this is the outline, the talk. I've got the luxury of talking fairly late, and so what I thought I'd do is pick up on what different people had mentioned in their talks, and show you how you might draw some pictures related to that, to those works. Okay, so we've seen quite a few examples where people are doing supervised classification, and as part of that dimension reduction, find a nice low-dimensional picture of the data that tells you everything you need to know. We've seen that in a number of different talks. I'm going to use olive oil's data to show that we really would like to do more than just the best projection. David Donahoe mentioned the 4D cross polytope. I'm going to show you a few more pictures of that one. He showed you a couple of random projections, or a couple of projections, I don't know if they're random. And then we've been developing a library of high-dimensional geometric shapes, and I'll show you a few more different geometric shapes as well. And we also have developed a game called Face Off that you play in 4D. And I think it's fun actually to think about building up games on playing boards that are high-dimensional as a way of getting some intuition for high-dimensional spaces too. So I'll talk about a game called Face Off. And then I'm going to switch to cluster analysis, or unsupervised classification, and talk about self-organizing maps, which hadn't come up, I think, at all yet, which is a little surprising. And I'm going to show self-organizing maps on my music data that I've collected from my CDs. And then model-based clustering, which was mentioned in Werner Stutzler's talk. We look at the model. The model is ellipses, which parameterize which map to the variance-covariance matrices. And I'm going to use the Australian crabs data to demonstrate that one. And then finally, I'm going to switch back to support vector machines, supervised classification of support vector machines, and talk about looking at boundaries in well, it's not all that high-dimensional space. I also hope that I'll have a chance. Lutz showed the cigarette data and supervised classification of the cigarette data. And I want to show, if we get time at the end, I'll show what that data looks like in 10D. Is it 10D? Okay, so first data set. This is a pretty old data set. It's data collected on olive oil samples. There are 3 geographic regions of Italy. It's a little bit more complicated than that, but there's 3 the main classes are South, North, and Sardinia. I'm just going to look at 4 variables. There's a few more than that, but just for starters, 4 variables. And the question that people ask with this data is, do the olive oils from different growing regions have different fatty acid signatures? All right, so the 4 variables are fatty acids, and we're looking at the composition of the fatty acid in the olive oil sample. Right, so I don't know how many of you eat or drink, whatever you do, olive oil, but it's it's been touted more and more, I think, at least in the US. People are shifting from, I don't know. But the different fatty acids are supposed to be better for you than others. And so even though it's an old data set, it's a pretty interesting data set, actually. And I guess that's enough. Okay, so in the left plot here, pick your favorite dimension reduction method. This is where we plot our data in the model space. These are my 3 regions. I'm sorry, my colors switch a little bit from one to the other. That's because I'm using different software, and but I think it maps reasonably well. The purple here is the purple over here. The green here is the green over there. It's just the orange and the blue that have switched colors. All right, so it looks pretty good. At least this group is quite well separated from the other 2 regions, and so it looks like we can detect the oils from region 1 from the oils from region 2 and 3. And regions 2 and 3 look fairly distinct as well, although there's a little bit of a neighborhood in here where we might be a little bit confused. Okay, that's a best projection. That best projection is represented by this box, this rectangle, I should say, in the right-hand plot. I'm going to show you a little more than that one, so we're going to start the movie and show a few other projections as well. My movie works. Oh yeah, here we go. And now it's just 4D, right? And these are just random two-dimensional projections of 4D. And tell me what else you notice about the clusters corresponding to the three different classes. Pardon?
Green breaks into two.
Yeah, green breaks into two. This guy is a bit like a banana shape, just similar to what Werner was showing as an example. This one here was pretty much elliptical in every projection. Okay, those are a couple of interesting things we've learned that we didn't see from here. Okay. All right, so what do we learn? The orange cluster is curvilinear. The green cluster is composed of two clusters. The orange and green have a big gap between them. Did you see that? Anybody not see the big gap? So that's actually a really important one. The orange and green groups have a big gap between them, and it's not detected by the dimension reduction method. Actually, no dimension reduction method that I've found picks a view where there's a big gap. Right. So all of these are really interesting things that we just missed if we only tunnel vision into a particular projection and only care about whether we're getting the best prediction of the classes or not. Yes, it can be. All right, I'll run it again. And we'll come back to this data set at the end as well. You can slip a linear, but the boundary really looks non-linear. There's a curvilinear boundary between the green and the orange group, right?
There's also quantization.
Oh yeah, that's sort of a marginal effect, right? So if you're really interested in the data itself, that orange group looks like someone's discretized or measured the values to a certain resolution. Okay?
They also seem to be a lighter plane.
Oh yeah. Right, so I haven't said everything again. Right, those four variables, really, it looks like it boils down to, well, at least those two groups. Just 2D is enough to explain the variation in the samples from those two regions. Yeah, good observation. Okay. All right, so switching. I'm going to talk about geometric shapes. Our library of geometric shapes has been created by a 19-year-old kid at Iowa State, undergraduate student. It's pretty impressive, actually. And I'm going to show three things: cubes, face-off, and the cross polytope. I'm going to jump to the cross polytope, actually, first. Oops. So again, we saw a couple of projections, but this is the 4D cross polytope, what's sometimes called an octahedron, I think. And what David was interested in was whether those vertices are internal. He's only really interested in the convex hull of this. So when he says that a face disappears, it means that the vertex is interior. And it almost always happens, he argues, when you get to 4D shape. I don't see very many, I don't see any at all where all the vertices are on the outer shell. Okay, how many people have seen a 4D cube? 5D cube? All right, starting with 3D. This is going to, the cubes are really interesting because they just grow out of themselves as you grow dimensions. So they basically just double Right, and so as you go to a 4D cube, it's just the 3D cube doubled. Right, so there's our 4D cube. We often see pictures of 4D cubes. People in, I think, computer science draw them a lot, but one particular view. And way back early in the century, Hampel hand drew a 4D cube and used it to show a response to an experimental design. Anyway, so it's been done before, but anyway, we're almost up to 10D. It's very pretty, isn't it? It's very regular. It's very round. Yeah, right, right, you can think of each dimension being a Bernoulli distribution with equal weight on zeros and one, and then linear combinations of a 10D cube are basically, a lot of the views will be close to the average of 10 independent by Bernoulli random variables. And so yeah, it's sort of central limit theorem. It's not quite, because we've got linear combinations, we don't have the average. But there must be some relationship between that central limit theorem and linear combinations as well. All right, so it looked a bit spherical. What's the difference between that and a 10D sphere? These are points on the surface of a 10D sphere. Right, so there's a really nice trick to generating points on the surface of a sphere. You generate points on a univariate normal 10 times, and then you standardize the length, and then you've got a point that's uniform, uniform on a sphere. If you get really good, you can detect whether it's a hollow sphere and a solid sphere too, in what people have done, at least for lower dimensions, less than 10 dimensions. Okay, it's a little bit different. The cube has more points sort of in the outer fringe, and there's all these regularities. Let's see. Okay, the game of face-off is just like tic-tac-toe in 4D. You've got two players, and they consecutively or sequentially choose a vertex that they place their marker at, and your goal is to get a 2D face in your color before the other person does. Do you see any strategy going on here? Just like tic-tac-toe, you want to get into a position where you've got two possible ways to complete it. And so that's what the orange guy is doing. Trying to get 3 points on two different faces. And the blue guy is just blocking. You can spin it, of course, if you want to take another view. If you spin it, you can see the orange guy is almost won. Maybe it was a bit hard to see before. All right. I think that the way the game gets played is that it should always be a tied game, and only the first player really has freedom to choose which vertex to place their marker at, if they're smart. The second player really is slave to the position that the first player put their marker at. Anyway, it's kind of a fun game, and it evolved from just talking about games generally, and with an office mate, Dave Bulger at Macquarie University, he wanted to take a 2D board game and shift it up into higher dimensions. And we sort of struggled with how to do that, and this was sort of an intermediate step of taking a space and something similar. In the end, what he recognized was that that the 2D game that he was interested in doesn't have an analog in high dimensions. And so by playing this game together, we got some sense of, or he got some sense more of what the high dimensional constraints might be. Anyway, that's a cross-polytope. Okay, so switch again. This is a different data set. This is what I call my music data. And I've messed up some words up here. Actually, I'm going to use this to talk about self-organizing maps. That's not correct up here. It's self-organizing maps I'm talking about, which I also call fishing nets. And the data is data that I collected using my CDs. I've got some of these songs on here. I was going to play them, but maybe that's a bit too much in this crowd. So my CDs, I have some ABBA music, Beatles, Eels, some classical, Vivaldi, Mozart, Beethoven, and Enya. That sort of dates me. Enya's new wave, right? Anybody not heard Enya music? Oh, okay, can't help it.
Peter was first. I didn't want to embarrass him.
This just played, so I'm hoping the speakers work. Okay. Right, maybe it's not going to happen. Anyone who was sitting in here before would have heard some of that music being played, but I'm not going to mess around technically here. Okay, so I did this, I collected this data basically to create a data set that I could use in class for students that maybe they'd have fun with. And the basic goal originally was I've got 3 different types of music, or 2 mainly, rock and classical, and I only collected a few of the Enya songs, just for interest's sake. Because new wave, I think, ought to be a little bit rock and a little bit classical. So it might be a little bit of both. I'm going to use just 5 variables that summarize the time series. And originally I only clipped out the first 40 seconds of the music track so it wouldn't swamp my version of R. I used a package tuner to read the songs into R and then process that time series. And the basic question that I had originally was, could you separate rock and classical? Actually, what the students were given was a data set that had 57 cases and 72 variables, where we had left and right channels, and they had variables measured from the periodogram. And so it's an interesting large p, small n problem originally. I was curious to see how they would reduce the dimension. It turns out it's not so hard, and really 5 variables of all of those, really simple ones like the average, the variance, and just a couple more are enough to distinguish rock from classical music. But for this, I'm doing clustering, and so the question is, how is the music from different artists and types similar or different to one another? Okay, so just a clustering of the music clips. If I use self-organizing maps, then what is a self-organizing map? It basically, it is a clustering method. It's just like k-means clustering, if you've heard of k-means before, where you say that this data has 10 clusters, you estimate the means, and then you cluster cases into the closest mean to the closest mean. It's a constrained k-means in the sense that what you fit to the data is just like a fishing net. So it's generally a two-dimensional grid, and you throw that into the high-dimensional space and wrap it around and warp it through. But those nodes in the fishing net are the means that you group cases to the nearest means. And the reason why people like it, I think, is because you can take that 2D grid that's been warped through the high-dimensional space, lay it flat on the, straighten it out on the table and lay it flat. Okay, and so you'll get a view of your data that I call the map view, just like this. I haven't got all the titles spelled out in here, but if you could, I don't know whether you can see the grid. I use a 6x6 grid, and so there's little, very faint white nodes at the back here. Those are the means in the knots in the fishing net. And I just use color and the name of the artist, well, not really the artist, but the composer. Here, Vivaldi, Mozart, Beethoven, and purple is the rock, Eels, Beatles, ABBA. ABBA seems to be out on its own. That comes through from the data as well. And then there's a few Enya tracks in here as well, which is sort of on the cusp. There's one Beatles track that gets mixed up with the classical ones, and that's Hey Jude. Anybody know Hey Jude off by heart? No. Do you know what's at the start of Hey Jude? Anybody? There's piano music at the very start. So I just looked.
What happened to Eleanor Rigby?
Eleanor Rigby's somewhere down here. I don't know. Okay. All right, so starting from this one here, this is the map view. I'm going to go into, so what people do is just look at the map view. What I'm going to do is take that fishing net and show how it was fitted to the data finally. The left-hand side here is just using the defaults for the SOM package in R. And although there wasn't much different from the map view, this really looks like it hasn't been fit to the data at all. It just looks like a sheet has been placed through the data. Okay. After quite a lot of work, you get to this view over here. I had to play a lot with the convergence criteria. I was a bit surprised that I had to do so much work to get sort of a reasonable fit. Let me run that again. Okay, there's not a lot of difference in the map view. I know. But clearly the fit to the data is much better over here. You see the fishing net sort of curved in amongst the curve in the data. The data's got some pretty interesting structure in it. There's some outliers. Some Vivaldi tracks are outliers, and there's, I think, one Beethoven, and then a couple of Eels songs are also outlying. There is a little bit of a curvilinear pattern. There's a small cluster of ABBA tracks which I can't detect. I haven't got them marked here. All right, so the key point here is people don't look at this view of the model in the data space, but it's really quite interesting, right? I really can't depend just on the defaults. I need to work a lot in order to get a better fit. And even then, this fit's not great, right? If I get the feeling that I want to pick up some of the parts of the fishing net and drag it through different places where the net hasn't fit, subspaces where the net hasn't fit the data very well, right? Okay, so that leads to another thing. One of the problems that I have is that the SOM algorithm in R doesn't allow me to look at the different stages of the fitting. What would be really nice is if we could actually watch the fishing net get wrapped through the data, okay? Maybe intercept the algorithm, change it to do something different. But the current function that we have that's available in R doesn't allow any sort of intermediate steps to be examined, okay? There's a new package called Cahonan, which after some discussion between Hadley Wickham, who's also sort of working in this area, and the author of that package, they've made it possible to have intermediate steps printed out so we can watch the net being wrapped through the data. And we can also calculate a lot more diagnostics at different stage. Okay, so what did we learn from this? Defaults to the function didn't result in a good fit. Wasn't obvious from the map view. It may have been somewhat obvious maybe from studying the estimate of the error from the fit. You can get that out of the algorithm. But it's funny that we had to play with the convergence criterion to get the better fit. And it still seems that there are some neighborhoods in the data space where it doesn't fit very well. All right, so that map view that everybody uses doesn't provide a good assessment of the fit. I think these are all important things to know for fitting the model. Self-organizing maps are extremely popular, right? I don't know whether you've hit that or not, but they're very, very popular. And I don't really know why, but I've got some suspicions. One is that it gives this convenient dimension reduction. But we have other ways to do dimension reduction, a lot of different ways, right? You can do principal components analysis. This would be the view of the data in the principal components analysis as a comparison. Which of the two is more accurate to the structures that you saw in the data, do you think? I mean, if you're going to take that 5-dimensional space and create one 2-dimensional space which best summarizes the structure that you saw in the 5D.
Excuse me, have you done scaling before the principal components on the right? Tangent components?
Yes, I think it was done with the correlation matrix. Yeah. Yeah. All right. Just run it through again. So when I've got, see if you can mentally summarize the structure in the 5D space. Right, there's some non-linear dependencies, curvilinear dependencies. There's some outliers. There's some sort of skewness, the points clump up. Those are the key features of the data in 5D. Right? So which of these summarizes that better? This is the more accurate 2-dimensional picture of the 5D space. Right, we've got a few of the outliers. We've got a bit of clumping. But it's a pretty ugly view, right? This is a really pretty picture. You don't see any of those features. You don't see the outliers. You don't see the clumping so much. But everything's sort of nicely spread out so you can look at it. You don't have things overlaid on one another. Right? I don't know, but yeah.
One could argue that you do wish to see things overlaid. If you think about, you would like similar stuff to be very closely together. So ugliness is good in this aspect.
Okay, it's good to keep yourself looking at the world through rose-colored glasses, right? Maybe not, but I mean, there's something pleasing about looking at the world through rose-colored glasses, and I think the SOMs are a little bit like that. But actually, I have to admit, when I was doing a final summary of this data in my case study, I used this view as a summary of the clusters as well. Partly because, you know, in that really old-fashioned way that people do summaries of clustering and also classification, they put little convex hulls around the cluster. I could do that in this picture. I could put a little convex hull around cluster 1 and cluster 2, cluster 3, and it gave me a sense for how cluster 1 was similar or different to cluster 5. Okay? And that was possible here, but it wasn't possible over there. I know. But they're very popular, they're very cute, but they also try to solve too much, I think, try to do dimension reduction and clustering all in the same big bag. All right, switching again, it's still talking about clustering. We talk about model-based cluster analysis, and essentially what we do with model-based is model the clusters using elliptical structure, different sorts of elliptical structure, and simple or more complex means more, less or more parameters to estimate in order to fit the model. The data that I use here is another old data set. It's called the Australian crabs data, and the groups, right, so I'm going to pretend that I don't know the groups, right? This is a classical setup for studying cluster algorithms. Get a data set that was used for supervised classification and do clustering and see if it can uncover the groups that we know about, because it's really hard to assess clustering methods without having some truth. Okay, so my classes are species and sex of these crabs. There are 5 variables which are physical measurements, and basically we're interested to know if any clustering algorithm can recover the 4 groups. It's a pretty interesting data set again. And most cluster algorithms can't handle this. Partly the reason this is because there's a very strong association, linear association between all 5 variables, right? Small crabs are small in every dimension. Big crabs are big in every dimension, right? So small crabs have low values on all the 5 physical measurements, and big crabs have big measurements, big values on the 5. I'm just starting off with 2D here. So two variables of the 5 and 2 classes, male and female, for 1 species of the crab, just for starters. How you usually would evaluate the model-based clustering is to calculate BIC over any number of clusters, various numbers of clusters, and you pick the model with the highest BIC value. Right. So here it would suggest that the best model has got 2 clusters, and the variance-covariance parameterization is EEV. That means equal variable. You say it's equal elliptical. It's basically what it means, but the ellipses are rotated. So the EEV model is equal ellipses for each cluster, but they're angled differently. Right? So they're angled differently, which looks like a great model for this data, because here's cluster 1, here's cluster 2. It's not quite elliptical variance-covariance structure in that data, because there's less variation down here than up here. Right? It's a bit of heteroscedasticity. But this seems like model-based should do a pretty nice job of dealing with it. Werner's method, I think, would have trouble with this because they're not really well separated clusters. At least small crabs, it's hard to distinguish male and female for a small crab. When they get bigger, it's a bit easier to distinguish male and female crabs. Okay, but the BIC suggests the model looks great. 2 clusters, equal elliptical, just different orientation, which I expect that those ellipses are sort of joined down here. One goes up this way and one goes up that way. But if we look at what the estimated ellipses are, it's not that at all. So it's a bit surprising. This is that model. There's the ellipse corresponding to the variance covariance for 1 cluster, ellipse corresponding to variance covariance for the 2nd cluster. And they are different orientation, but they're also shifted. Right. So that model doesn't look good. It doesn't capture what I expected it to capture when I say it doesn't look good. This is the best model for this data in my views, at least matches better with my eyes. We've got 1 cluster for small crabs and 2 clusters for big crabs. And that's the EEV3. That's this guy. Slightly lower BIC, but it makes a lot of intuitive sense. with this data. Okay. Let's jump up to 5D. Let's see if we can do the same thing in 5D. It's a fairly long video. Right, so we've got 4 classes. The orange species is yellow and orange. The blue species is purple and blue. Some of these colours might not be as easy to see as others from the back. This is going to take a little while just pointing them out. When we start rotating, the overall structure in this data is that strong association between the 5 variables. Small crabs are small, big crabs are big. And so there's this long cylindrical shape to the data. But the 4 classes really are quite distinct, actually. Let's watch this rotate for a bit. And see if you can get a mental map of what the clusters look like. Anybody like to describe the cluster structure? If I gave you 4 pencils, could you arrange them in a way that would match this structure? Pretty much. I didn't bring 4 pencils, but maybe I can borrow a couple. It's like, it's a bit exaggerated, but they're sort of joined together. Not quite, actually. If you look closely, it's 2 joined together and another 2 joined together at one end. And the species are distinct. It's just the sexes that are small crabs are connected. And then they fan out at the other end of it. This is a pretty interesting shape. Okay, but that's what makes it really difficult for any clustering algorithm. So this was just sort of an exercise for me to see whether any cluster algorithm could detect those 4 groups. And if any did, model-based clustering is a pretty good chance of doing that. So we fit model-based. I'm not going to show you the BIC criterion, but I picked the second best model here, which was 4 clusters and the EEV again, right? So that seems like a good model for this data. Equal, elliptical, variable angle, different orientation to see. That sounds good. Let's see what those ellipses look like when we put them into the data. So there are 4 ellipses in here, all represented by grey. These are 5-dimensional ellipses. We're just going to look at the shadows of them. So each view is going to be just 2-dimensional ellipse. There's no matching of colour to ellipse. When you're doing clustering, we're not saying that this group, this cluster is this group. So I've just coloured them all the same grey. And starting off, you can't see the model very well for the data here, which is a good sign. It says that the model matches fairly closely to the data. I'll turn the data off in a moment. Okay, so can you see 4 ellipses rotating around? There's a few that are sort of overlapping. So it's like 3 are almost overlapping in one sort of direction and one's on its own. It doesn't match up to what I expected it to do either, even though it looked good from the model model estimation or the model diagnostics. This doesn't catch those 4 groups. And so I'm still at the point where I haven't found any method that captures those 4 classes. Okay? Ready for a break? Yeah, questions?
So do you have any way to say, do research about the use of these tools to improve instruction or improve communication? So that do we know that students who get exposed to these things have a higher rate of continuing on to be majors or make higher scores on tests?
Or get more accurate results in their data analysis?
Yeah, well, what do we know about it? Because obviously it's a useful tool, but do you know of research like by people in perceptual psychophysics?
You know, I think we really need to start measuring these things, but then you need to design some experiments where you really can take a group that's taught with and another group without. But I, in all honesty, would not be able to teach without using these tools. I couldn't with good conscience. So my multivariate analysis classes are all the way through, in the data mining class, all the way through, we look at pictures along with each of the methods. And the students often come out with generating their own software, at least in data mining, generating their own software to monitor some of the different algorithms themselves. So, it just to me, it's just a no-brainer. I can't possibly operate. This is how I understand problems. I have to draw the pictures. Maybe, I think that's not true for most of the people here. You have your own way of developing a conceptual map. But this is my way. If I can draw a picture, and if I want to fit a model, this allows, with the R and Gigobi combination, allows me to sort of be an engineer in a way, to build a model and then mold it. Build a prototype, basically. And then, I don't know, I'm not sure I'm answering your question here, but
No, it's very useful. I just, for example, I taught an introduction to probability recently. Book had almost no picture. And I did use the computer sometimes to illustrate things like books for forming central limit. But it seems that I didn't choose the book. It's been used in the department for some time. I used to use a book with more pictures, and then I was away for a few years, and people have been using this other book. And so in instruction, it seems that this technology, although it could be used heavily, is sort of not making the inroads one could imagine.
so there's someone who started off with Max Spin way back when.
Yeah, but I'm interested in, do we have any understanding of what our goals are in instruction and whether we're getting there better one way rather than another? And is there some way to formalize this and reach real conclusions?
Well, I mean, I think that's becoming expected now in instruction anyway. And generally, I don't think we've done a good job of monitoring statistics instruction, see how well we're teaching students. Maybe the first year classes, there's a lot more measurement that's going into teaching Statistics 101, which I think has improved that course over the last decade dramatically. At least our 101 classes are amazing, I think, at Iowa State. I don't know, but I mean, it's a really important thing to start thinking about how to measure the effectiveness of your teaching.
I hope I'm not, monopolizing discussion. I do have one
There's
other.
another question here. Yeah, or comment.
Just out of curiosity, what is it in your view that makes a clustering persuasive? Is it a well-defined boundary? Is
Right.
it stability property? Is it a margin?
Yeah, and then this is a key, actually, we'll move on to the next part here. This is related in a way to support vector machines too, because I've been looking at data for a long time and I see things that don't get picked up by the algorithm. But what I'm seeing is gaps. Visually, my eyes are cueing so much on gaps that's the main thing that I think you look for, right? And it's not what many of the supervised classification algorithms work from, right? Linear discriminant analysis looks at the means of the classes and the variance and assumes equal variance covariance around each of those means, and it builds a boundary on the basis of that, whether that exists in the data or not. Quadratic, you can vary the variance covariance. Neural nets put some sort of additive model, but support vector machines. The very goal of, or the mechanism for that is that find the points on the convex hull for each of the clusters or each of the groups, and build your boundary on the basis of those. So it really uses gaps between classes. And so what was really interesting for me when I first started looking at this is this one actually matches what I expect to see better than anything else. So, I mean, the eyes they operate in various ways, and I mean, I don't know that we understand a hell of a lot right now, but there's a lot of work in cognitive perception about how our eyes work. Here in supervised classification problems and clustering problems, it's the gaps that are the dominant feature, I think, that are detected by the eye. So support vector machines model the boundary between classes on the basis of those gaps, and it seems to match pretty nicely to what my eyes see. So going back to the olive oils data, this is just those two groups that were a bit harder to separate. This is the boundary for a linear SVM. It's just 3D, all right? It's not a big deal, it's just 3D. So that's the boundary generated by the support vector machine. It's a better boundary than what we'd get from LDA in the sense of looking at the gap. Right. People don't stick to linear boundaries or linear kernels is what they say in support vector machines. They like to do nonlinear kernels. This is a polynomial kernel, and that's a boundary that we get from that, which is pretty lousy, right? Because you have this really strange predictions, up here, predictions for that other group in the wrong neighborhood. Right? If we looked at the radial kernel, that's actually quite a nice boundary because it captures the nonlinear gap between those two groups we saw before. Okay, but the key point here is, again, we can do this in high dimensions. I didn't want to jump straight to that in high dimensions for this because it's a bit harder to look at boundaries in high dimensions, but we can. But the key point is getting the model into the data space to see how well it matches up with what we expect to see or what we've seen visually as well. Anyway, that's basically all I wanted to say. I do want to show Lutz's data. So one of the hurdles for visualization has been technology. I mean, every couple of years there's some different sort of operating system and different technology. And I think that's been one of the things that has slowed up research in visualization. The other thing is there's not enough people doing graphics work in academia, which is where you generate new students. So, you know, I think now is a great time because the technology is pretty mature and stable. And we can do things like script interactive and dynamic graphics from R, which really opens up a whole new world as far as merging modeling and graphics as well. So let me just show you, well, I had some things, no one mentioned inference. So I had actually a couple of things I wanted to say about inference and small n, large p too, but I'm going to jump out of that. If anyone's interested, we can talk another time. Now, this is the data that Lutz said on the different cigarettes. So I've got those different cigarettes over here as a bar chart with their names. And these are the 10 variables. I'm not sure whether this one here, GES amount,
It's just the sum, I think.
so just leave that out.
Yeah,
Okay,
leave it out.
that's what I had. All right, and so we'll watch this with some random tools as well. I've got one group highlighted. Take that off. Can you see the purple? The reason why we use the dark color is because it originally is because you really want to be able to change focus and focus on small groups. So I've got brushing going so I can look at individual groups. But for starters, what's the structure in this data? Predominantly. It's pretty linear, right? So there's a pretty strong association between the 10 variables. And then there are a lot of these little clusters all over the place, a little bit of nonlinearity too. If we take a look at some of those groups, I'm not sure whether class 1 sort of matches up to what you had, but that one's pretty distinct from everyone else, that cigarette type. Here's another one that's pretty distinct. This one might be a bit harder to classify. It's a bit mixed up with another group. Actually, maybe we want to go back over here and see which of those cigarettes that are more similar to one another in that they're clumping in the data space, what they correspond to in terms of the different brands as well. Right, so this would provide another way to look at the data to say, yeah, it's pretty hard to separate cigarette A from cigarette B or whatever. Okay, I think I'll quit at that point. Thanks very much for listening.
Are there any further, quite a lot?
Yeah.
I'd like to pick up on what David spoke earlier. I think I come down on this a lot closer to your side than anything else. I use graphics an awful lot, and I teach a class, an advanced class, in graphics. And one of the things we learn in that class is how to fit regression models by eye, by just looking at plots with no objective functions. And we can do that for 10, 15, 20 predictors. So we have very, very high dimensional, but we can go in a lot higher dimensions than 3. And what I find is at the end of that class, the students tend to trust your graphical fits, the graphical summaries of the data, more than they would trust a model. In the sense that if a model gives something that's drastically different than what they see by eye, they will tend to question the model before they question the graphics. I think there really is something behind this. The approach that I take is somewhat different than yours, and I think maybe it can be expressed by using your analogy of crossing Mattingly Avenue blindfolded. Imagine instead that you just arrived in London at 9 o'clock in the morning from the States. It's 3 o'clock in the States. You have a little buzz on you, and you decide to stay up the whole day, as many people do, and you go out for a long walk. Well, this is your first time in London, and you don't know anything about it. So you're walking around London, and you're processing things in very, very high dimensions. Now, there are a couple of dimensions for you that are absolutely crucial. And one is when you cross the street. Now, you might figure out that that dimension is important, sort of by hit and miss and watching what happens. But I am very, very grateful for that sign on the street that says, look left. And so what we try and do is find signs that look left. Now, every time I come to London for the first time and I see that sign, look left, I'm grateful for it. But I can't keep myself from looking right as well. It's impossible. I want to know that I should look left, but I also have to look right. And it's that ability to know when you should look left and concentrate in that direction, I think, that that can take this kind of graphical stuff and push it a step forward so that you can be more comfortable in what you're getting out of it.
There's a couple more.
Based on the sides, well, it depends on which side of the street you're on. Sometimes, if you're on a divided highway.
There's a couple more things to say. One is, this software didn't take 1 minute to program. Right? It's taken decades to get to the current state of where we are. Two is, a lot of the graphics work that you do is sort of under the hood, like a lot of what the R core group do is under the hood. It's hard to be able to say, tag, this was used to get this result. So it's harder to quantify in a way, but it's absolutely vital. I mean, there's a great quote by an English guy, I think it's Chatfield, in his book. It might not be Chatfield, someone else, I think. When talking about initial data analysis, whenever you're doing a data analysis, and particularly the initial data analysis, which in the British sense means checking assumptions before you fit your model. So, but in the exploratory data analysis sense in the US, maybe more predominantly, it's also discovering unexpected things. But he says there is no excuse for ducking that stage in a data analysis because you might end up with a red face at the very end. It's just a really lovely quote, I think. It's hard, I think, to be more thorough in studying things from all sorts of different angles. It's much easier, I think, to spit out a p-value. In some ways, it's not. It's sort of human nature, I think, to want to have a single little answer without all the nuances of a problem. I don't know.
Well, I agree with all the philosophy that actually that both of you have said. I just was observing, instructors who are trying to teach, especially so students can perform on a test. Many of them seem to not be persuaded or to not bother or whatever. And so a lot of students never get the chance to see what you're showing. A lot of instructors never use these materials. And I don't know what would persuade them or what changes in the teaching culture.
I think making things easier for people. You've got to have materials readily available for people to use,
It's fantastic that you've created these tools and that they can be just downloaded and installed, and it should be something of great benefit. How do we get it more heavily used?
So one of the things that we're working on, this library of high-dimensional geometric shapes, this is, I think, for mathematicians that you can go to and pull something out and take a look at it, whether you've looked at it before or not. And if we can get more shapes in our library, I think that's good. But developing more teaching materials is also the next stages of what we're doing, because the RGGobi software is pretty stable and mature right now too. It doesn't crash as much as it used to, and it's pretty easy to install. So there's less and less excuse not to get something like that running. And there's other packages like iPlots too, which get you into interactive graphics. But getting that teaching material together to show people how to, because they haven't had it themselves, is another key part. I don't know, yeah, Ben.
I have a small thing of a technical nature. So in many of the plots that you were showing, scatter plots, you mentioned that gaps are important. I think also the eye naturally sort of sees the convex hull of groups very naturally. And then there's the problem when things, let's say, don't completely separate and they're kind of noisy and confused. How to help the eye see what's going on by supplementing the graphics.
Exactly. I didn't show any of that here in a way, but in some time putting the model on or putting something on, like allowing a person, we can allow a person to draw on the plot, draw lines, so that they see something, then they can mark it and guide it and the shape of the future. But that is important to have supplemental information on the plot to help guide people's eyes to it. Scatter plots are too raw for many purposes. Didn't?
I just wonder what's your experience with data with like hundreds or thousands dimensions?
Right. So this I didn't show that because, and people have talked about this all through the meeting, is sparseness.
Can you repeat the question?
So the question is, what's my experience with data that's got hundreds or thousands of dimensions?
Yeah, high
Right. If you've got a small amount of data, you can't do much better than the marginal distributions. You've got thousands of variables. Your data's sparse. I mean, you can give me data like that and you tell me what you want to see, I'll find it for you. Okay? I don't want to be looking at linear combinations. It's sparse data, marginals, just single variables. It's going to be best.
But that's the theory. But in data, you might not have sparsity. So you want to confirm sparsity.
Right. So if you have a huge amount of data as well as a large number of variables, yeah, you're really in a tough spot. Right. But you know, you can't look at scatter plots. So I'm talking about large N as well as large P now. You can't look at scatter plots because you've got too much overplotting. You need to then do densities of some sort, but then you have to compute those as well. So, but in then large dimensions is another issue on top of that as well. Maybe I heard that you had an interesting problem
Yeah,
that you
I'd like to
talk
look
about
at
sometime. Yeah.
I think perhaps without seeking to curtail discussion, I'm sure there'll be plenty of opportunity to request replays of your videos later. But for the time being, we should thank you again.